In this class, we will discuss the Gomory's cutting plane method. As I have told you, we have the method of solving linear integer programming problems. Okay, there are several methods, but we will in our syllabus we have Gomory's cutting plane method. So let's go. Gomory's cutting plane method. So you know the yes, I have we have already have the concept of what do you mean by linear integer programming problem, all integer programming problem, and we have discussed that with our graphical representation. So in that graphical representation, actually, suppose let me consider the graphical solution, that is feasible region, like this. So it looks like this. So in two variables, x1 and x2. So x1 x2 plane, we have the solution like this, and we have the vertex, I mean the feasible region like this, the first quadrant, and the a, okay, a, right, and b, okay, b, then c, d, then a. This polygon is our feasible region, right? So and the vertex will be our optimal solution, but we got f is equal to the optimal solution for our objective function 34.5, then 5 half 5.5 and 4.5, but it is not our integer solutions, right? That was our problem when you are solving using simplex method, dual simplex method, or something like that. Okay, but we want our integer solutions. So how to do it? How to get integer solutions? That is what we are going to discuss in Gomory's. That is our method of Gomory's cutting plane method. Okay, so in Gomory's cutting plane method, actually what we are doing is, yes, we are uh, finding the optimum solution, all integers optimum solutions would that would result in a optimum value, that is integer value of f. Okay, so for that, what we are doing is we are introducing a new constraint, a new constraint is being introduced so that so that the optimal solution will become, once solving the LPP, you will get all integer solutions. Solution will become all integers. So this is our aim, and this newly introduced constraint is known as Gomory's constraint. Gomory's constraint. Okay, or Gomory's cutting plane also we will call it. Why? Because cutting plane actually that is named like that for three variables, x1, x2 and x3, three decision variables. So in that case a plane is considered, but in this case x1, x2, two decision variables, we have lines. That means we have the Gomory constraint like this, some uh, 2x1 plus 3x2 equal to some 5 or something like that you will get. So this is nothing but 3x2 equal to 5 minus 2x1 and x2 equal to 5 by 3 minus 2 by 3 x1. So this represents a line. So this is Gomory's, suppose this is Gomory's constraint that we will introduce something 2x1 plus 3x2 less than or equal to 5, like that. Okay, so that this is nothing but our line equation. So Gomory's cutting plane or cutting line you can say in two decision variables. So we will introduce this constraint to this feasible region, okay, to this feasible region, so that we will get our new optimal solution, which will be all integers, absolutely all integers. If you, that means graphically, if you see this 5.5 and 4.5, that would result in f equal to 34.5, which which is not at all acceptable for all integer LPP. All right. So what we will do is we will find out a set of points in which that set of points all are integers, like your points given in this region. That means these points, okay, uh, black dot points, all these black dot points, suppose say this is P, this is Q, point Q, R, S, T, U, V, W, X, etc. All these points subject to the same constraints will result in all integers, right? So if you take this this x point, then this point is nothing but your 1 5. So x1 x2 is nothing but x1 1 and x2 5. So this is all integer solution, right? All integer solution. So and w we will get 2 5 2 5, like that. Okay, like that. All these points are known as lattice points. Lattice points. So one of these lattice points will be our solution. One of these lattice points will be our solution. So in order to find out that, we will introduce a new constraint which is known as Gomory's constraint, and this Gomory's constraint, like this we will introduce a constraint. A constraint means, what do you mean by a constraint? Constraint is in this case will be a straight line, okay, like this. Okay, so we will introduce a constraint, it is less than or equal to, so again this region, okay, that means, okay, this region we will get, means, yes, this has got reduced, right? That means this yes, this red feasible region, actually it is cut off, it is avoided, it's been cut off by this Gomory's cutting plane, right? So that our feasible new feasible region got reduced. So in that way we will introduce one Gomory constraint. If it is not giving all integer solution, then we will again introduce another Gomory constraint, okay, another Gomory constraint, so like this, uh, so that yes, a larger portion of feasible region is being cut off. Okay, cut off like that. We will introduce that much number of Gomory constraints. Gomory constraints. Okay, Gomory constraints, so that our solution will become all integers. Okay, like that. For example, if you, yes, let me consider a Gomory constraint in the form of a straight line like this. Yes, this let it be G1 and G2. This is our Gomory constraint. Okay, so in this case we have cut off this much of area, right, from our initial feasible region, and we got this. We are Then what we will do is we will check the vertices and all the points in this feasible region, and if any of these point result in a integer solution, like point here, that is, which is 54 point 54 point. Okay, that 54 point is all integer, and this all integer you will substitute in f, and if you get this f and you got it as 31, that means it is also an integer, right? So all the conditions for an all integer LPP is satisfied in this case. So in that case, this Gomory constraint will give our all integer solution. So we will stop there. Okay, so we will get the solution all integers, and also it is also minimizing our objective function f equal to 31. Okay, this is our concept. Hope you understood the concept. Now, suppose we have the okay, we have the general form of a LPP. That means you have solved, you have the LPP, solve the LPP minimizing f is equal to, we have the cost coefficient C1 x1 plus C2 x2 plus etc plus Cn xn. Okay, subject to the constraints, we have the constraints like this, right? A11 x1 plus A12 x2, that is the general form. Okay, that is what I am writing, plus etc plus A1n xn equal to b1. So like that, sorry, not b1, it is not equal to, it is some less than, let us say. Okay, less than, and the standard form. Okay, so and we have a12, okay, a21 a22 etc, then m1 x1 plus am2 x2 plus etc plus amn xn less than or equal to bm. So this is our general format, let us say like this, and we will proceed this LPP problem with our simplex method. With our simplex method we have proceeded, and we got, after the completion of all the iterations in simplex method, what we got is, that means we got a unity. You will get, after the successful completion of simplex method, what you will get is f all positive, and all f row entries are all positive, okay, then only we will stop the simplex method, right. So that you will get. And also this our the basic variable x1 x2 etc xi up to xm, and this basic variable matrix, the matrix corresponding to this basic variable will be an identity matrix, right. Why? Because we will in if you recall your simplex method, what you will do, what we are doing in that is we are finding out the pivot position or pivot element, and we are making all the elements or entries in that particular column 0, and the pivot position unity. So like that, at the end of or the at the completion of simplex method, you will get an identity matrix like this. You got like this, okay. And I have the non-basic variables. The basic variables I have, and I have the non-basic variables also. Non-basic variables I have, I am calling it as y1, y2, y3, y4, etc., yj, etc., yn. I am calling it as, and its coefficients will be arbitrary. I am taking this as a11, a12, a1j. Actually, this bar, that means this is nowhere related. A11 bar is nowhere related to your a11. Okay, it is nowhere related to this a11 bar, a11 and a11 bar. Okay, it may be related or may be equal or may not be also equal. And okay, so a11 bar, a12 bar, a1j bar, a1n bar. So you got the all the corresponding coefficients also of y1, y2, etc. Okay, and yes, this is your objective function column. Then constants we have, that means your bi star, that's solution column. Okay, so this is our okay. Up to this we will do in all LPP, whether it is all integer LPP or any kind of LPP, we will proceed up to this LPP solving. Okay, our general method of LPP solving, that is our, we will apply our simplex method or dual simplex method or two-phase simplex method, or like that you will apply, and you will reach here, you will reach like this. Okay, and you found that this x1 solution, which is our b1 bar and b2 bar, b3 bar, okay, b3 bar, etc., x1, x2, x3, etc., are fractions, some 11 by 2, some 7 by 2, some 3 by 2, like that. Okay, like this. But our x1, x2, x3, x4, etc., xn must be all integers. That is what our linear integer programming problem. So this is not acceptable. 11 by 2, 7 by 2, 3 by 2, right. So in that case, what we will do, what is, we have already said that we will introduce Gomory's constraints. Gomory's, yes, this beautiful Gomory's constraints. Yes. So next we will discuss how to construct a how to construct a Gomory's constraint. Okay, yes. So from our table, the first step in constructing for the construction of Gomory constraint is you look or you observe your table. That means your table is this table, table 10 to 10.2. Okay, this you observe your table and choose the basic variable with the largest fractional value. That is, you observe your table which you got after the completion of your yes optimal, that means your optimal table. Okay, the table corresponding to your fractional solutions, fractional optimal solution. Okay, so that table, you observe that table and you find the basic variable which is having the largest fractional value, for example, this you have to observe this bi star column, b1 bar, b2 bar, etc. Okay, that you have to observe. And this suppose I got it is 11 by 2, okay, then 5 by 2 I got, then minus 3 by 2 I got, and 4 by 3 I got, like that. Okay, then you 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 first of all consider all the positive values, you ignore the negative value minus 3 by 2, you ignore it and consider only the okay, not only the sorry, you cannot ignore this negative values also, but you have to consider the magnitude. Okay, magnitude of all these fractions you have to consider. So 11 by 2 means some 5 point something, 5.5, right? Then 5 by 2, 2.5, then 3 by 2 is 2.5 you will get, then 3 by 2 magnitude if you take, you will get 1.5, and then 4 by 3, 4 by 3 is 1 point something, 1.33 or something like that. So then you find out the maximum fraction value out of these values. Here the maximum fraction value is happen to be this 5.5. So you choose that row, okay, that corresponding row, and you will find suppose this 11 by 2 is this b1 bar. b1 bar is equal to 11 by 2. So this, the row corresponding to this is the row corresponding to our basic variable x1, this x1. So this x1 you have to choose it, you have to choose this as your uh, this uh, this basic variable you have to choose. Then what you have to do, I will tell you. And if when there is a tie in the fractional values, when there is a tie, that means it is happened to be this b2 bar is also 11 by 2, suppose it is also 11 by 2, then there is a tie. So in that case you can choose any of them, you can choose. Okay, any of them you can choose. So I'm taking here an arbitrarily I am taking that let xi be our basic variable corresponding to largest fractional solution, right? uh, okay, largest fractional solution. So in that case I'm writing it as xi, you have to write it as this xi, okay, is equal to pi bar minus sigma j. I'm introducing a new variable, that is j, and that is varying from j equal to 1 to n, up to n, then ai j bar y j. Right, this is our equation. And where this bi bar is a non-integer. It's a non-integer. And this we can write this non-integer as bi bar is equal to some b is okay bi cap plus beta i, where this bi cap is an integer a okay an integer. It's an integer, and this beta I is fraction. Beta I is a fraction. That means if you got this 11 by 2 as bi bar, okay, bi bar is equal to 11 by 2 suppose, then I have to divide, or I can separate this into sum of two numbers, and this is this two numbers. One number will be the our integer part, and the other part will be called as fractional part. That is 11 by 2 means what? 5 plus 1 by 2. So this is our integer part, that is nothing but our bi cap, and this is 1 by 2 is our beta I, that is our fractional part. Okay, so this beta I will be greater than 0 and less than 1. Okay, and this bi cap will be uh, integers. Okay, integers, positive integers, exactly positive integers. Okay, and this is our bi bar. That means this 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 value, and we have to define this. Now we have to define this aij bar, this value. What is that value? That value actually, again, you can represent this aij bar as equal to, in a similar manner we can write it as aij cap plus alpha ij, where this as like your 11 by 2, like your 11 by 2. That means aij bar is, suppose we have this is some 5 by 2, then you can write this aij bar as 2 plus 1 by 2. That means this aij, this is aij cap, and this 1 by 2 will be alpha ij. So alpha ij will be greater than 0 and less than 1, like our beta I, and this aij cap will be a integer, right? An integer. Yes. Okay, so we define these two, and what is our aim? Our aim is to create, okay, create the Gomory's cutting plane, or Gomory's constraint. So our aim is that. So if you get alpha, if you get this alpha ij, beta I, then aij bi, aij cap and bij cap, then the Gomory constraint will be the Gomory constraint will be like this: Si minus sigma j equal to 1 to n alpha ij yj equal to beta minus beta I, where this Si equal to a new slack variable. So this is our Gomory constraint. This is our Gomory constraint. So once, that means once you once you yes, once you yes, first of all you will get yes, step by step we will recall it. First, what you have to do? First you have to find out xi. You have to find out. Then, so how to find out this xi? That you know from your tabular column. Then you have to write it, this xi, in terms of bi bar and aij bar and yj. You have to write in this manner. And once you will get this bi bar and this aij bar and yj you will get, and from that you will get this bi bar can be written as yes bi cap you will get, and this beta I you will get, and similarly you will get aij cap and this alpha ij also you will get. Then you have to introduce the Gomory constraint by introducing a new slack variable Si, and Si will be equal, and the new Gomory constraint will be Si minus sigma j equal to 1 to n alpha ij yj equal to minus beta I. So this is okay. So uh, you will get more clarity while we are solving a problem. So we will move on to, so yes, once you have this once you have this Gomory constraint, then what you have to do? You have to apply this Gomory constraint in your previous table. That means you have to introduce this new Gomory constraint in which table you have to introduce? You have to introduce in yes this table, this 10.2 table. You have to introduce the Gomory constraint here as right as a row. That means here you will get Si, and you have to write the corresponding coefficients of x1, x2, xi, xm, okay, and etc. like this. Okay, so that is our general approach, and now we will take up a example problem and we will meaningfully we will understand it. So our problem is minimize So example, okay, once you introduce your Gomory constraint into the table 10.2, then what you have to do is you have to solve for it. Okay, like that, if you introduce new Gomory constraints, then what you will observe is you will observe all these optimal solution, that is for x1, x2, x3, will converge to all integers. Okay, so example problem we will take up. This is minimization problem. So minimize f is equal to minus 3x1 minus 4x2. Minimization problem in two variables, and subject to subject to the constraints. After introducing slack variables or surplus variable, we got it like this: 3x1 minus x2 plus x3 equal to 12. Then 3x1 plus 11x2 plus x4 equal to 66. Then xi greater than or equal to 0, I equal to 1 to 4. I varies from 1 to 4. Then all xi are integers. So once this statement, if you meet with this statement, then you can conclude that this is a linear integer programming problem. So you can solve by Gomory's cutting plane method. Okay, so our step 1 solution, we have solution. Step 1, sorry, step 1 is, like we have discussed, solve the LPP as if it is not a linear integer programming problem. Okay, using simplex method. So if you solve that, if you after step 1, what you will get is, yes, you will get the, after the completion of your simplex method, the tabular the table looks like this. That means you have the basic variables x3, x4. Okay, x3, x4, then minus f, then we have x1, x2, x3, x4 coefficients like this, the matrix like this. Okay, then okay, actually this is not the there is a mistake. Actually this is the starting, right? The starting, or yes, the starting of your simplex method, by considering the basic variables are as your slack variables x3, x4. Yes, right, good. Okay, so you will proceed like this. Okay, first you will get like this. That means uh, s3 s3 minus 1 1. That means your first equation 3 is corresponding to the first row. That's 3 minus 1 1, then 0, then 12, like that. 1 0, then 0 12. Okay, that means you have to perform your simplex method in you have to write that in standard form or canonical form. You have to write it, and you can write the tabular column. Okay, so this is your first table, and then a second table looks like is after getting your pivot element, then you have to make it as 1 and all other entries 0. Okay, then entering variable, leaving variable, so that you know to explain further. So you do that. Okay, and the uh, next table will look like this. So this is your after the updation of previous table, you will get this table. Then again you will find out the leaving and entering and leaving variable, and again you will update the table, and you will get the table as yes. So the table looks like this. So if you observe this, these are our basic variables. Okay. Then x1 x2 x3, like that. Then okay, then you have this bi star, that is solution column. So x1 star, we got it as 11 by 2, and we got x2 star, we got it as 9 by 2, and my f is equal to minus 69 by 2. So that means our conclusion is that we cannot take this 11 by 2, we cannot take, and 9 by 2 is also not possible, and so this f, this is also not possible. So what you have to do, you have to construct. So the next step 2 is construct a Gomory's constraint. So our Gomory's constraint will be, for that you have to find out what you have to find out, xi you have to find out. That means, then how to find out this xi? You have to observe the solution column, you have to observe, and you have to find out of this these basic variables which is having the maximum value of fraction, maximum fractional value. So that is the row corresponding to x1. Okay, you need not to look this minus f row. Okay, only our basic variable you have to, that means you have to find out xi. Okay, so check this x1 x2 row only, and the maximum fractional value out of these correspond to 11 by 2. So x1, okay, xi equal to x1 and I equal to 1 you will get. So x1 is our yes variable. So that variable, you have to write that variable like yes, like this, xi Okay. Sorry. We have the equation. We have xi uh, xi xi equal to vi bar minus sigma j varies from 1 to n aij aij bar yj. That means I am introducing new variable yj. Okay, and if you, in this case we have xi equal to yes, bi bar is nothing but your b1 b1 bar, that is nothing but yes, this b1 bar. So that is equal to 11 by 2. Then you have the ai, yes, aij bar y1 y2 y1 and y2, 11 by 36 and 1 by 36. Okay, so we have here, we have the basic variables. Here we are defining the basic variables, right? X1 and x2. So x1 x2 we will get, and we have x3 x4 also. So the non basic variable, yeah, uh, so this is our updated table with Gomory's constraint that we will write here S1 by yes, by taking the basic variable the new basic variable we are introducing in the Gomory's constraint, that is s1. So new basic variable s1. Okay, so yes, now in what way you have to proceed, you have to update this table, that is our next question. So for that you have to apply dual simplex method here, dual simplex method, to find the new optimum solution. Why? Because here actually what happened is we got the optimal solution by performing simplex method itself. We got it right. That means the minus f row is all non-negative, that is either 0 or positive values. So we cannot proceed with simplex method further. So in that case what we will do, we will go for the dual simplex method. We will go for dual simplex method. So in dual simplex method what we have, yes, we have to find out the entering variable as well as leaving variable. So for leaving variable, so the concept is just interchanging. That means you have to find out not the in our simplex method we found the pivot column, but here we have to find out the pivot row. So in this case that means the most negative value in the bi column, that is in the solution column. So that is nothing but your s1 row. So this will be your pivot row. Okay, then next, so that means this s1 will leave, s1 will be the leaving variable. So if you have any doubt you can go to the dual simplex method that we have already explained it. So I will not explain it more. Why? Because it is a waste of time. So yes, so what we will have is, then we will get, yes, the leaving variable we got it as s1, and then we have to find out the entering variable. So in order to find out the entering variable we have to add another row, that is ratio row, we have to add it. And adding ratio row means this row divided by the, yes, this row can be filled like this, uh, yes, the corresponding elements of this pivot row, okay, divided by minus of the corresponding elements of f, minus of, sorry, not that, actually c the coefficients of objective function, that is yes, cost coefficients. So cost coefficient ci divided by negative of our pivot row elements, corresponding elements, minus a r s. So what you will get is 0 by 0 not defined, 0 by not defined. So you will get 7 by 12 divided by minus minus of minus 11 by 36. That will be equal to 7 by 12 into 36 by 11, that you will get 21 by 11 for the for. So here you will get 21 by 11, and for y2 column we have 5 by 12 divided by minus minus 1 by 36, that is what plus 1 by 36, so that will be to equal to 15. So this column will be 50, then not defined. Okay, so and for entering variable you have to uh, consider only the positive values, and from that you have to select the minimum value. So minimum of 21 by 11 and 15 is nothing but 21 by 11. So this will be our, that means y1 will be our entering variable. So the next table will be like this. So this will be our new updated table. So if you observe, this solution column is getting all integer because x1 is got integer. Okay, so x1 x2 all will converge to integer value. So yes, then we have the, yes, this here the our slack variable s1 is got replaced by this y1. Okay, and what we will do is we will pivot that pivot position, which is this y1, right? So yes, by row operations we will do it like this. So after all this we will get like this. Yes, now, yes, again if you observe again the solution column, if you observe, x1 is 5, that is integer, x2 is 51 by 11, and y1 is 18 by 11. So again we have not got the all integer solution. So what you have to do, you have to introduce again Gomory's constraint, again a new Gomory's constraint. For that you have to construct a new Gomory's constraint. So for that again I have to find out xi, in which, that means the basic variable which is having the maximum fractional value is nothing but your either 51 by 11 or 18 by 11. So which will be, yes, is x2 equal to xi equal to x2. So I is equal to 2. Okay, then you have the, yes, I'm just uh, short I'm skipping all the previous explained steps. I'm directly writing the x2 as x2 equal to, like, in terms of your, right, okay, then we will get 51 by 11 minus 1 by 11 by 2 plus 3 by 11 s1 plus 3 by 11 s1, where, okay, you will get alpha 1 1, alpha 1 2, beta 1, sorry, beta, not beta 1, it's actually beta 2, and alpha 2 1 and alpha 2 2 for I equal to 2. Okay, alpha 2 to beta 2, all this you will get from our table, because here we have the, again we have, okay, let me explain that once again. We have b, yes, we have b2 bar. b2 bar b2 bar means x2, this is equal to b2 bar. So that is what here we have written, b2 bar. Then we have a the matrix corresponding to x1 x2 x1 x2 y1. So basic variable, non-basic variables, this matrix you have to consider. Yes, this matrix excluding this minus f column, exclude. So this will be your a11, a12, a21, a22. So a21 1 by 11, that is what we have written here. a22 we have written here. Okay, 3 by 11, this is actually, yes, y2 s1, y2 s1, yes, because we have considered the y2 column and s1 column. So this will be y1. Previously we have y1 and y2. Okay, which are the non-basic variables in the previous case. But in this case we have the non-basic variables as y1, sorry, not y1, y2, right? y2, that means y2 is not in this column in here. Okay, so y2 is non-basic variable and s1 is also non-basic variable. So that is this. And then you have to consider this 51 by 11. You have to fractionalize this. That means 51 divided by 11. You will get 4 or 44, then 7. So you can write 51 by 11 as 4 plus 7 by 11. So this will be b2 cap, and this will be beta 2. Okay, so you got this beta 2, and also similarly you can have for a21 equal to a22 equal to a21 bar and a22 bar. So a21 bar is 1 by 11. A21 bar is 1 by 11, and a22 bar is a22 3 by 11 minus 3 by 11 minus 3 by 11 or 3 by 11. So this will be your alpha 21 and alpha 22, because only the fractional part exists here. Okay, yes, so you will get the second Gomory's constraint like this: S2. That means we are introducing the new slack variable for the second Gomory's constraint, S2 minus 1 by 11 y2 plus 3 by 11 s1 3 by 11 s1 equal to minus 7 by 11. So this is nothing but just substitution. Okay, and then the next step is we will introduce this new Gomory's constraint in our table. and we will proceed with our dual simplex method. Then we will get this table. Here if you observe, you can notice that s2 as a new basic variable, and this s2 row, okay, you can fill by with the help of this equation 1, x1 coefficient 0, x2 coefficient 0, then yes, we have y1 coefficient 0, y2 coefficient minus 1 by 11, then s1 coefficient we have, then minus f coefficient 0, s1 coefficient 3 by 11, and this s2 coefficient 1. Then we will again proceed with our dual simplex method. Dual simplex method, if you apply, you have to find first, you have to find the leaving variable. So in order to find out that, you have to check the bi column, the solution column you have to check out, and you will notice that the most negative number in that column is minus 7 by 11, and that corresponds to s2 row. So this is our pivot row. Pivot row is this, and this will be our leaving variable s2. S2 will leave uh, in the next table, and entering variable will be, in order to find that, you have to fill the ratio row. Ratio row you have to find out. So that will be not defined, not defined, not defined, and 4 by 11, 4 by 11 divided by minus 1 by 11, so it will be 4. Then not defined, then this will be some negative number, so if you can discard that negative number. So, and here we have this will be our, so this 4 will be our minimum positive value, and you will get as y2 entering variable. Then after pivotization, the updated uh, table will looks like this. And yes, now if you observe, if you compare the basic variable and the solution column, okay, what you got is, what you will get, you will get all integer or all integer solutions. So you can stop here. The given solution will be our optimal solution for linear integer programming problem. So x1 is 5, x2 is 4, y1 is star 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 is 1, and y2 is equal to 7, and f is minus 31. Okay, so this satisfy the integer requirement of the problem. So this is our desired solution. So with this, we have completed our module 3. So we have remaining, we have completed 1, 2, 3, and 4. So we have 5 and 6. So in the next class we will enter into 5. So thank you.